Okay, volumes of revolution, which is your next section. I find that some students have just fine. They're just fine with visualizing this, and I find that other students have a really hard time visualizing this. So in the past, I've actually brought in supplies to the classroom in order to help students visualize this. We're gonna try and see whether that sort of lecture is actually effective when we're doing it by YouTube video, and you can give me some feedback as to whether this is actually the case. Now, what happens is we are given, let's say we're given this f of x right here, and let's say from A to B, I want to find the volume as if I had revolved it around the x-axis. Now remember when I told you that integration is not the area under the curve. The area under the curve is just happens to be the first application that you actually learn about in terms of integration. But integration is a means of accumulation, okay? And all you have to do is figure out how to cross-section it. Now, when you were dealing with the area under the curve, the cross-section was simply the it was simply a rectangle, right? And that's how we reasoned out that if we were dealing with the area under the curve, you went from A to B, you were summing up. Remember, there's a reason why the integration symbol looks like a big S. You were summing up from A to B the infinite number of cross sections that had a height of f of x and a width of dx, right? So this was this was height times width. And basically, this represented any and all of the cross-sections, the infinitesimally thin cross-sections from A to B, and then you were just summing them up, okay? Well, we're going to do something similar, but we have to figure out exactly how to change, right? How to change what we're doing. Now, let's go ahead and look at this. And if you're saying to yourself, is that a cutting board and a knife? The answer is yes. Your powers of observation serve you well, okay? Now, once you take that region of f of x and spin it around the axis, you're going to have a volume, okay? And that volume is going to have cross sections. And those cross sections won't necessarily all be of the same size, right? But they will all be of the same shape. They will all be what are called discs, okay? And after we're going to go ahead and cut all these up, I'm going to go ahead and explain it to you. Now, look. Now, of course, they're not perfect. These are two separate cross sections, okay? One of them is larger than the other. They are, however, both circular, okay? And they're both circular on the edge, but you see that they have volume. They are cylinders, okay? So what we need to do is we need to figure out how to represent the infinite number of cylinders that we're going to be accumulating with integration, and not the infinite number of rectangles, okay? So we're looking for a formula that's not f of x times d of x, where it's not just height times width. We got to figure out how to do this. Now, here's the question. When we're dealing with the cylinder, what was our f of x? Okay? And the answer is, and let's see, I'm actually kind of curious whether this will write on here. Here's the thing. Your cylinder actually there's your f of x. And that didn't work too well, but you see it a little bit, okay? There's your f of x. Your f of x is actually the radius, okay? So if we know that that's the radius, and of course our width right here is still our d of x, this cylinder was created, and I'll get back to this. That cylinder was created by the area coming off of the the plane and spiraling around. Okay. Now, this is a region. This axis that runs right along here is x, and we're going to actually spin it around x, but let's first spin just one of the cross sections. That's a rectangular cross section, and if I were to want to actually get the area, I would accumulate all of those cross sections. I'm going to go ahead and send you this. I'm going to send you this, the link to this site, so you can go play with it yourself. And I would just basically sum up from 0 to 1 all of those rectangles. But if I want the volume, that is going to spin around and create that cross section, and I'm going to need to add up the infinite number of cylindrical cross sections. We are not dealing just with area anymore. We're dealing with volume, okay? Because that region comes off of that plane and actually goes all the way around. See, it just kind of, and I hope that helps you sort of see it, right? That comes off and actually completes that revolution and creates, it almost looks like a conical frustum, except for it's kind of curved just a little bit. Okay? That is basically what we're doing. And in the midst of it, and in order to get that whole volume, you're going to have to get all of those cylindrical cross sections, okay? All of them. And that means that we just have to figure out how to represent it. Like I said, when you're dealing with integration, it is a matter of accumulation. That accumulation is actually relatively easy once you have a way of determining how to represent the cross sections. If you figure out how to represent the cross sections, then from there, it's just the mechanics of integration that you already know. So really, the hard part is setting it up. Let's go ahead and look at another one of these. Okay, no, not that one, not that one. Now, sometimes, and of course, you know, if we are looking for the area of this particular one, I would actually look for the sum of all the infinite number of rectangular cross sections, right? And I would add up all of those, and it would just be the integral from a to b of f of x dx. But if I want to find the volume of that, I need to add up the infinite number of cross sections that are cylindrical cross sections. And in this one, they're not discs, they have a hole in the middle, and they go by the really technical term washer, okay? Discs are to washers as area under the curve is to area between the curves, okay? And what happens is I get this region right here. I mean, I get this volume, and of course that volume is the accumulation of all of those cross sections, and we just have to figure out how to represent them, okay? Here's another one. Okay, let's go ahead and revolve the region. That region is arrived at by those infinite number of cross sections that are not rectangles, but the cylinders that are generated when those rectangles are spun around that axis. Okay. Last one. We've done that one, we've done that one, we've done that one. Yeah. Now, we will eventually get to a point where we're not spinning them around the x-axis, but we are spinning them around an alternative axis. And that shouldn't freak you out. It's just we just have to do a little bit of subtraction in order to represent the radius of those cylindrical cross sections or washer cross sections just a little bit differently. So it's all about figuring out how to represent the radius or the radii in the integrand. And at that, once you get that down, it really is smooth sailing from there. It's just a little bit difficult to sort of see it in your mind's eye if you don't have representations like this. And I can't even. I mean, I'm pretty good at visualizing things in my head, but I can only imagine people that aren't, how they did this before there were sort of internet animations and stuff like that to help them along the way. Now, I haven't chewed up that much time, but I want this to sort of be the sort of intro to it. I'm going to go ahead from here now, and instead of area, the volume of revolution is simply going to be, since this is going to spin around like this, okay, and is going to have that width right there. The volume of revolution, since I've already told you that your f of x is your radius, is going to be pi r squared, right? Because the volume of a cylinder is pi r squared h. Your r squared becomes f of x squared because that's the variable representation of our radius. And your h, since we're really taking, the cross sections, and to think about it in terms of a cylinder, you just have to take, this and turn it this way, right? And then you see it's the height, but the height, when you flip it back up, is really your dx, okay? And so h becomes our dx. And that right there is why the volume formula is what it is. And this, of course, is used for the disk method. When we get to the washer method, which is very, very just like one logical step away, I'll go ahead and introduce it then. The next video, we'll just jump right in with some examples, and we'll move forward from there. Okay.